Okay, welcome back from your break. This is the second video in the Reynolds transport theorem and radial hydraulic jump lecture. We stopped on this slide last time, but it was a good stopping place because we're about to transition to the next presentation objective, which is for me to explain, at least qualitatively at first, why hydraulic jumps form, and then to show you guys the analogy between hydraulic jumps and sonic booms. So what actually causes a hydraulic jump? Well, it turns out that there are two important velocities, and it's the ratio of those velocities that really tells you about the formation of a jump. The first velocity is the rate of surface wave propagation, which we'll refer to using the variable c. And that variable c dictates the rate at which information is transmitted along the surface of a fluid. And really the way to think about this is to think about a clear, quiescent, calm pool of liquid, and then what happens if you drop a stone into that pool of liquid. So I use this image to dictate this situation. So initially this fluid is calm, and then you drop a stone here in the middle of it, and the surface waves propagate outwards from that disturbance location to indicate that there was some sort of disturbance, if this stone was dropped into this otherwise calm pool of liquid. Well, the leading surface wave, which moves away from the point of disturbance at a velocity of c, the rate of surface wave propagation, carries with it the information that that stone dropped into the pool. So any fluid between the point of disturbance and the leading edge of this first wave is aware that that stone was dropped into the pool. But any fluid that's out here at a radius beyond that leading surface wave is still not yet aware that that stone was dropped. That's why the fluid out here hasn't responded by somehow creating a surface wave or some sort of disturbance of its own. It's simply not aware that the stone was dropped because the surface wave hasn't propagated out that far yet. So this is a case of essentially water that's standing still, but you can actually induce velocity in a fluid, and that velocity, which we'll call V sub flow, has the potential to exceed the rate at which information propagates in surface waves. And so it turns out that these two velocities can be combined into a ratio, the ratio of the flow velocity to the rate of surface wave propagation, and that ratio turns out to be so important in fluid mechanics that it's actually been given a number. It's called the Froude number. Froude was an early fluid mechanics researcher, and the Froude number again is this ratio between the rate at which the fluid is actually moving and the rate at which surface waves propagate in the fluid. So the Froude number can have essentially one of three values. It can be greater than 1, which is so-called supercritical flow, which means that the fluid is flowing faster than information can propagate along the surface of the fluid. What happens in that case is that if there's any disturbance, any upstream disturbance in the fluid, the information about that disturbance cannot propagate because the fluid is flowing faster than the rate of information propagation in that fluid. And so when the fluid actually reaches the disturbance, it responds instantaneously to the presence of some disturbance that it didn't know was there before and forms what are essentially shock waves. The other possibility is a Froude number that is less than 1. This is so-called subcritical flow, and in subcritical flow the fluid is moving slower than the rate of surface wave information propagation, and so if there's a disturbance in the fluid, in the flow knows about it in advance and can essentially get out of the way. So it creates a wake pattern instead of a shock wave. So to give you kind of a physical sense of what these two fluid regimes look like, I've got these images down here. So this is an image of subcritical flow. So this is a river flowing around a rock that's sitting in the river, and as you can see, there's this bulge of fluid out in front of the rock. The water is flowing essentially from left to right across your screen. And so this bulge of fluid forms because the fluid is moving slowly enough that the presence of the rock can be propagated upstream, and so the fluid knows that the rock is there, and it can essentially form that bulge, get out of the way, and create this subcritical wake around the rock. So that's one extreme. That's subcritical flow, Freud number less than 1. The other extreme is supercritical flow, which is a Freud number greater than 1. And this is essentially a bullet being fired out of a gun. Bullets travel at supersonic velocity, and so this bullet is traveling faster than the speed at which information can propagate in this fluid. And so what happens is all the fluid that's upstream of this bullet has no idea that the bullet is coming, because information about the bullet's presence can't be propagated upstream because the bullet is moving faster than that rate of information propagation. And so as a result, when the bullet arrives, the fluid is not aware that the bullet was coming, and so it responds essentially through a shock wave by being jarred from one thermodynamic state to another without really having any way to prepare for that. So you get these kind of bow shock waves that come off of the bullet, but notice there is no separation between the nose of the bullet and where the shock wave starts, because the fluid upstream of the bullet had no idea that the bullet was coming. Now, the third regime is where Freud number equals 1, and that's essentially the transition between subcritical and supercritical flow. And it's at that regime transition between these two different types of fluid flow where we see hydraulic jump behavior. So that's essentially the explanation as to why hydraulic jumps form. They essentially are the barrier between subcritical and supercritical flow in a flow field. Okay, so here is the Cedarburg River again, and I can show you now with slightly more informed eyes what it is exactly that we're looking at. So fluid spills over the spillway here, and it's moving very quickly. It's actually moving at faster than the rate of surface wave propagation, and so the flow here is supercritical. And then there's this barrier here, which I'll explain in a moment, and then over here the fluid flow is very slow, and so this is subcritical flow, where the fluid is moving slower than the rate of information propagation in the fluid. Now, this boundary between supercritical and subcritical flow, well, that is the hydraulic jump, I will show you actually in the next video actually some moving footage to show you that this hydraulic jump is essentially a steady state phenomenon. It's fixed in location, but this hydraulic jump essentially demarks the difference between the supercritical flow and the subcritical flow. The last thing that I want to point out here is if you look at the structure of the fluid, it's kind of this weird scalloped pattern here and this much more calm quiescent pattern here. Those two different fluid patterns are indicative of here the fluid is moving faster than information propagation, and here the fluid is moving slower than information propagation. So here it's responding almost instantaneously to every small disturbance, whereas here it's not responding that way because it has an opportunity to get out of the way. Okay, so I've reached and exceeded my 7 minutes, so I'll stop there. Please take a break and come back, and we'll pick up this lecture in the next video. Thanks. See you soon.